We move on to the last speaker of the session morning. So last speaker is Sebastian Moore from Quantemol company in London, who is going to speak about plasma chemistry and chemistry set optimization approach for atomic layer deposition and atomic layer etching modeling. Please, Sebastian, you have the mic and you can share your screen.
So thank you for the introduction, and thanks to the organizers for giving me the opportunity to speak here. And I'd like to talk about our approaches to generate and optimize chemistry sets with a slight focus on ALD and ALE. So this presentation is not so much about film growth directly, but rather about how to get good data from plasma simulations, which can then, for example, be used in surface simulations to simulate the film growth. Before I get to the talk proper, let me maybe first introduce our company, Quantemol. We are a company affiliated with University College London. And essentially what we do is that we transfer academic research to non-experts, for example, in industry, but also in other academic fields who want to use, for example, plasma simulations, but are not numerical plasma physicists themselves. And essentially our three areas are calculation of cross-sections for molecules, so electron scattering cross-sections, plasma simulations based on the HPEM code by Mark Kushner, and then collecting and curating plasma chemistry data. And this presentation will focus on the third point, which is actually a rather vital step in setting up a plasma simulation. And rather this, that we can, if you look, for example, as an issue which can arise in plasma-enhanced ALD, whose goal it is to grow thin films with a higher level of precision, which, however, does not always work perfectly. You see, for example, in such trenches with high aspect ratio, you can get a lot more deposition in the upper part of the trench than you get at the lower part of the trench, whereas what you actually want is a uniform deposition throughout the entire trench. And now how these profiles look like depends, of course, on the fluxes of species generated in the plasma. For example, radicals generated in the plasma or in the plasma environment are also ions. So what you want in the end is to find process conditions such as power and pressure, which give you a large amount of species which contribute to the film growth while minimizing the fluxes of species which can potentially damage the film. And this is something where simulations can be a rather helpful tool. For example, you can use these to test changes to your reactor geometry before actually implementing them. You can use them to optimize an existing recipe by, for example, doing a parameter variation in the simulations before moving on to experiments, or to get a better insight into which processes actually generate the specific particles. Or you can simply kind of test new gas mixtures or precursors, or you can use simulations to get a kind of preview on which species you can expect a specific gas mixture to generate. Of course, how well this works depends on how you set up your simulation. In order to get a predictive model, what you need is, first of all, a fitting physical description of all the phenomena which take place in the plasma. And additionally, you need chemistry data. And for these, first, you want to have, of course, enough chemistry data on species and reactions, which describe all the processes which are involved in the production and also destruction of your reactive species. But on the other hand, you also want to be able to run your simulations within reasonable amounts of time. And in complex gas mixtures, you can usually reach sets which have dozens of species and hundreds of reactions, which is not so much of a problem for 0D simulations, but when you move on to 2D simulations, such large sets will slow the simulation significantly down. So what you actually want is some kind of optimized set, which means the smallest possible set of species and reactions, which still gives you precise results with regards to the densities of reactive species. And this is something where we are active. And what we did here is that we kind of developed a suite of software tools which you can use to at least somewhat automate, for example, this reduction process. And this is based on the skeletal reduction approach, which is, for example, described in this paper by Lou. And what you actually do here is that you make an initial run with your full chemistry set, so all the reactions and all the species you have found in a 0D model. And then you use an algorithm based on graph theory, which ranks the species on how much they contribute to the production or destruction of your reactive species. So you get a kind of order. You order them by how much they contribute to the production of species. And for the actual reduction, you can go through the species step by step, starting with the lowest ranking one, remove this from your set, repeat the simulation to check if you stay below a maximal allowed error. And if it is done, you continue, remove the next species, and so on until you reach species whose exclusion lead to deviations above your specified error tolerance. And if you're more interested in more details about this approach, we have submitted a paper about this to PSST, which is still in the review process, but you can contact us if you're, for example, interested in a preprint publication. And to show you how efficient this approach can be, let's look at an example of an N2H2 plasma, which is, for example, used for the atomic layer deposition of cobalt layers. And we took here a set used by Hong, which is quite comprehensive and includes 42 species, especially as it includes a lot of excited states and positive ions. And this set was actually done for rather high pressures. So we transferred the set to the rather low pressure conditions, which are typical for ALD applications, and of species which we are interested in. And so the species for whose densities we want to preserve through this reduction process, we selected the NH2 and NH3 species, as according to Hong, these play a rather important role in determining the qualities of the produced film. So when we run this through our reduction algorithm, we're actually able to reduce the set from 42 species to just 19 species, which is a much more suitable number for multidimensional simulations. And as you can see, species which were eliminated by these methods are mainly excited states and ions, which might play an important role at higher pressures, but not at the low pressure conditions we are looking at here. And when we compare now the results from the reduced reaction set with the one from the detailed reaction set, you see that there's virtually no difference between these two sets, although we cut the number of species in half and therefore can accelerate multidimensional simulations by quite a lot. Now, you can use these tools, which are in this suite, not only to do the reduction, but for example, we have this species ranking method and other some diagnostic tools, which you can also use to analyze your chemistry set, for example, to identify important reactions, such as surface reactions, which are kind of the bane of plasma simulations, because data on them is relatively scarce, and they also tend to vary a lot depending on the type of surface and also on the actual process conditions with the same type of gas mixture and surface. So these are actually rather used as fitting parameters in plasma simulations rather than as precise inputs. However, they do play an important role. To stay in this N2H2 plasma, we have seen that these NH3 or NHX species are important, and they are actually almost exclusively used by plasma surface interactions and not by gas phase reactions. So in order to get this right, you need to find the right coefficients for your plasma surface interactions. And now, while we are not there yet that we can predict them or estimate them better, you can use these tools to kind of at least identify the reactions which actually contribute to the creation of these species. So you know which reactions you can actually use as fitting parameters. And this is done by doing a sensitivity analysis via the Morris method. Basically what is done here is that you make a lot of simulation runs. When each run you vary the coefficient describing one of the surface reactions. And this gives you then kind of a lot of different runs, each with a different set of return coefficients, surface coefficients. And then you can see, kind of statistically see how much the specific surface reaction contributes actually to the production of these NH species. And when we do this for our set, we see that actually out of the 9 surface coefficients we put in initially into our set, only 3 actually have a significant influence on the NH species. So for further evaluations of the set, we know now that we can concentrate on these 3 reactions and more or less neglect the other 6. Of course, you can do something similar also in the gas phase. As long as when you have kind of chemistry sets of a sufficient complexity, you will at some point kind of reach species for which you have no data. Specifically, for example, no electron collision cross sections. For example, in SF6O2 mixtures, the atomic O reacts with the SF radicals and forms these SOF species for which there simply is no reliable data on cross sections. You can of course simply go ahead and then, for example, calculate cross sections for each of these species, or you can first run some analysis and see if any of these molecules contribute significantly to, for example, in this case, the density of atomic F as the species which react with the surfaces, and if any, which, and then kind of just calculate cross sections for these. To do this, we collected a set for an SF6O2 chemistry set where we use estimated cross sections for the dissociation and ionization of these SOF species based on the respective cross sections for the SF radicals, and where we also assumed that when it comes to dissociation, each dissociation reaction simply knocks off 1 F of the molecule. Then we did a small parameter variation with the set and ran our species ranking scheme, which we also use in our reduction approach, to see if any of these SOF species actually contribute significantly to the production of electrons and atomic F. And we found here some process conditions where we actually see that SOF4 and SOF3 rank highest. So in this set, SOF4 and SOF3 basically contribute most to the production of both electrons and atomic F, which means, of course, that if we use only estimated cross-section, we introduce a large error into our simulation. So in the next step, we calculated cross-sections for SO4 using our quantum chemistry software package QEC. You see a comparison between the estimated and actually calculated cross-sections, which you can see quite a lot. And additionally, we also found while doing these calculations that the more likely dissociation pathway through SOF4 is actually not to SOF3 as initially assumed, but to SOF2. And when we implement now these changes into our model and compare it to our results with the estimated cross sections, here as a function of the oxygen flow, you see that there's a large difference in the electron density for some O2 mixtures. Is up by a factor of 4 or 5, and also quite significant change in the atomic F density. And additionally, when we do our species ranking again, we now see that SO3 is actually not amongst the highest ranking species anymore. So by doing this analysis first, we not only improved our simulation by using very precise instead of estimated cross sections, we also eliminated the need to calculate cross sections for SO3 and therefore saved a bit of time. Now, as mentioned, you can always come into the position where you need data, which you simply can find, mostly for some exotic species. And what you can do then, because there's some difference between heavy particle collisions and electron scattering reactions. For heavy particle collisions, you are mostly still kind of reliant on estimates. And here we are looking in how these estimates can maybe a bit improved by using machine learning techniques. We currently have a PhD student working on that, but he just started, so this is still a very early stage. For electron scattering reactions, there do exist some methods to calculate those, such as the matrix goes for molecule scattering cross sections. Of course, we are always happy to help. And one place where you can maybe start looking for data, for this I'd like to refer to our Quantemol database, which started just as a kind of collection of plasma chemistry data, so reactions and their rate coefficients for heavy particle collisions, and cross sections and weight coefficients for electron collisions. However, we kind of are in the process of amending this mere collection of data with some tools. Maybe I can show you what we currently have. For example, we have here this kind of chemistry set generator on our website, where you can here select your feed gases, for example, as in our prior example, N2 and H2. And yeah, then you can generate a list of species, other species, which can potentially be generated in this gas mixture. For example, you have N and H as dissociation results, and then the NH species via further reactions. And then in the last step, you can generate a list of reactions which can take place in this collection of species you selected. Then you can select which reactions you want to include, or simply be lazy and click here select all. And when you want to continue, we have currently 2 tools online with which you can do some calculations with these sets. First of all is here Boltzmann solver, which you can use to calculate EDFs and rate coefficients. For the gas mixture, we can also vary the relative densities to, for example, simulate different degrees of dissociation. And we have an online global model. We can here set your process parameters as pressure, power, and so on, gas flows, and which then gives you here the densities of your species as a result. And we're currently looking into ways how we can amend this further with putting our tools for analysis on the website. And just as a note, basic versions of these tools are actually available for free. So if you want to try them out, you can simply sign up to our software and get started. So then to conclude, what I've shown in this talk is, while simulations can be a helpful tool in enhancing your process parameters or to get data for simulations of surfaces, it is important to have a good chemistry set, which means that it is small enough to run simulations in a reasonable amount of time, but which also includes all important species and processes. And I've shown you some of our techniques we use to generate such sets. For example, the chemistry set reduction or the skeletal reduction. I said, if you want to have a look at our database, just go there and sign up. And I'd like to thank my colleagues, which you see here at our last year's Christmas celebration. And especially I'd like to thank Martin, who worked on the chemistry reduction and is now looking into the machine learning. Maria, who did the cross-section calculations, and also Anna, who kind of helped me with some of the slides. I'd like to say thank you for listening, and if you have any detailed questions, you can simply email us. And thank you for listening.
Thank you, Sebastian, for this presentation. Very interesting. Is there any questions? No, everybody is hungry. It's time for lunch. We are a bit late. No question on simulation. Maybe I can ask a question about, do you have any connections, or do you use some results that have already been published on the simulation of plasma from the Portuguese groups or from many other groups, or using the database that already exists?
No, sorry, I didn't.
I was wondering if you were using some databases on processes and cross sections that already exist, for example, for the base LXCAT in France, or no?
Yeah, of course, some of the data we have on our database is mostly from freely available sources, which includes academic papers, but also other databases. So we kind of collect data from all kinds of sources.
Okay, thank you. No other questions, so I would suggest that we close this morning session. I would like to thank all the speakers from this morning, because we are late, but this is because we had a very interesting speech, very interesting presentation.